How do humans adapt to new environments and situations, from cavemen to modern society? Are we given a data set of all possible scenarios in our life and labels that represent the ideal action that we take? Well, not really. Instead, we start from nothing and slowly gather memories and knowledge. And this is the idea behind reinforcement learning. In reinforcement learning, the model receives no labels and no data set, and it must gather experience from knowing nothing in the beginning. QLearning follows a process called the Markov decision process. And in a Markov decision process, an agent, or the model in this case, observes the state of the environment and makes an action. Then it receives a positive or negative reward. In QLearning, an agent creates a Q table, a two-dimensional list with dimensions equal to the state space and the action space. Each value on the list represents the quality of the respective state of performing the respective action. This Q table represents the whole decision-making process. Simply choose the action with the highest quality when in a given state. The Q table starts off blank, but as the agent makes more moves and gets more experiences, the table is updated according to the Bellman equation. The quality of an action, or the value of an action on the Q table, is equal to the reward obtained from performing that action, plus some fraction of the quality of the best next action that I can take. The issue is, the Q table has a size dependent on the state space. So if the state is made out of several thousand pixels, each being a value between 1 and 255, the Q table would be massive, and learning would be very slow. Deep Q learning is a technique to imitate Q learning in very large state spaces. So, in other words, Deep Q learning imitates the very complicated function, mapping states to actions. And you know what's also very good at imitating complicated functions? That's right, a neural network. But first, before any of the neural network learning, the agent runs around the environment and performs random actions, and it collects experiences based off of them. We store the experiences in an experience array. For each time step, we store the state, the action, the reward, and the next state. In Deep Q learning, instead of a Q table, we have a Deep Q network, consisting of many normal neural network layers and possibly some convolutional layers, if the input is an image. The output will not be an action, but rather the quality of all the actions that the agent can take. A neural network needs a target value to learn from, and the target value just comes from the Bellman equation, the reward plus the quality of the best next action. After some experiences have been collected, the neural network starts training. The input is a batch of random states from the experience array, and the output is the quality of all the actions it can take. The target is the reward that it gets, plus the quality of the best next action. The quality of the best next action is actually evaluated with a frozen network, similar to how a discriminator freezes when the generator trains, or a generator freezes when the discriminator trains. This network is called the target network. Once, as we so often in training, the target network's parameters will be set equal to the Deep Q network's parameters. The question becomes, how does this network actually perform on real-world challenges? And games have often been used to test the decision-making and problem-solving skills of agents, and many reinforcement learning agents have already achieved superhuman performance on games. This includes chess, the Atari games Go, and more recently, Dota 2.
4 dead on Team Human as OpenAI open the base up for a second set of racks, and GG will be called 21 minutes in.
So is reinforcement learning the first step to general artificial intelligence? Reinforcement learning, especially the Markov decision process, is an effective structure to making decisions about challenges that intelligent agents have to solve. By considering things like the state along with future state and rewards, reinforcement learning is in the right direction. However, it is still lacking in a few fundamental insights. In life, there is no way to define reward. There are no points in life, so an agent will have to give itself rewards as it sees fit. In reinforcement learning, the agent plays the same game over and over, but life is a bit different. We need to be able to transfer the skills from one game to another. If a human were playing a game, a good Pong player would probably be good at Atari Breakout, when they're playing on a rotated screen at least. Lastly, not all things in life can be learned with experience. Some things can only happen once. An agent would instinctively have to know not to drive off a cliff by understanding the world around it and predicting what will happen. In conclusion, reinforcement learning is an effective way to model the human thought process, considering states, possible actions, rewards, and future rewards. Deep-Q networks combine the idea of neural networks and QLearning, creating an agent that can adapt to large state spaces and action spaces. However, our current reinforcement learning methods are still lacking in some areas, and they're not ready to transition to general AI yet.